Let's do some problems. So here's the first problem. So suppose I have a finite group G. So let G be a finite group and let K be a field. Okay, so recall this notion of the group ring or the group algebra that we talked about. So the group ring is just what is it? Well, it's all elements of the form some linear combination, some coefficients Cg with some basis elements 1g. You can think of it as a vector space over the field K. Cg is coming from scalars K. Okay, but the interesting thing, as we saw, is that this is a ring and it's got multiplication, which is, well, one way of describing it is to say if I take these two basis vectors 1g and 1h, they multiply to give me the element 1gh. Okay, so this is a ring. So recall this whole business of opposites. So recall what the opposite of ring was. So if I have a ring R, not necessarily commutative, then R op is a new ring. Well, what is it? Well, it is firstly R as a set. In fact, it's R as an abelian group as well, the same plus. So I'll say same plus as R, but the multiplication alone is the opposite. In other words, the new multiplication A into B in R op is just defined as the product B into A in R. Okay, and we saw an example of the matrix ring which was isomorphic to its opposite because there was this transpose map, right? A going to A transpose for a matrix, it sort of changes the order of multiplication, right? So that gives you an isomorphism between the matrix ring and its opposite. So the first problem now is to show that the same is true of Kg. Okay, so prove that Kg is isomorphic to its opposite. So this ring and its opposite ring are isomorphic to each other. So in this sense, it shares this property with the matrix ring. Okay, so let's see what we would do. As in the case of matrices, the key point is to somehow try and guess what the map must be, something which interchanges the order of multiplication. And in the case of groups, so recall there is this important property of groups that if I take the inverse of a product, then that has the effect of changing the order, right? This is true if I have two elements of the group G, and so that's somehow the clue. We define the following map. So here's the isomorphism. Let's define a map from the group ring Kg to itself as follows. We take the basis element 1g to the basis element 1 sub g inverse, okay, for all g in G. Of course, if I define it on the basis on a general element, it's defined just as a linear combination, right? So summation Cg1g, therefore what I mean is that the map does the following. It takes this to Cg1g inverse for all G ranging over the group G. Okay, now the claim is that this map is a isomorphism between Kg and Kg opposite. Sorry, so what's on the other side is I'm thinking of it as the ring Kg op. And I claim is that this map psi is an isomorphism. So let's check all the properties. Claim psi is a ring isomorphism. So we need to check it preserves addition and multiplication. So addition is easy, okay? So because at the level of vector spaces, it's just a vector space. It's a linear transformation of vector spaces, right? So summation Cg1g goes to Cg1g inverse. So psi preserves addition is easy to check. So psi of alpha plus beta equals psi alpha plus psi beta for all alpha beta coming from Kg. So I will leave this for you to check. All you have to use is this equation star by star, okay, because both alpha and beta will have such expressions and you write everything out. The key point that needs checking is really this multiplication. So if I take a product of two elements, if I take psi of alpha beta, then I want the answer to be psi beta psi alpha, right? Well, I mean I want it to be psi alpha psi beta in kg op. I want this, right? So let's just check it on the basis elements. So let's take alpha to be the special element 1g, beta to be the element 1h, okay, fix two elements g and h from G. Let's see whether this is at least true on the basis elements. So when I compute psi on alpha beta, so first alpha beta becomes 1g into 1h, which by definition is 1gh, and therefore psi acting on this element by definition was just 1gh inverse, right? This is how psi acts. Now on the other hand, let's compute psi alpha psi beta, remembering that we are doing this multiplication inside kg op. So maybe I'll just put that funny symbol for multiplication to remind us that we are actually in the ring kg op. Let's go back for a second. So notice that the right hand side is kg op. So I take psi alpha into psi beta. What is this? Well, psi of alpha by definition is 1g, and I need to do this multiplication in kg op with 1h. So what is psi of alpha is 1g inverse, psi of beta was 1h inverse, right? Because alpha is 1g. Okay, but now remember this multiplication is in the opposite ring, which means it's the usual multiplication but in the opposite order. So this is because everything is taking place in kg op, and now we are done, because that by definition, so now these two things are equal, because let's check, 1 of gh inverse by definition is 1 of, so I know gh inverse in the group is h inverse g inverse, and 1 sub h inverse 1 sub g inverse is also equal to 1 sub h inverse g inverse, okay, because this is now the multiplication in the ring R, right? So I have already done the opposite, so I interchange the order of the factors and then I do the usual multiplication in the ring R, okay. So these two are of course equal, so we are done, okay. And of course third property we need to check is that psi of the identity is the identity. So recall that the identity of I mean the multiplicative identity of this ring is 1 sub the identity of the group, okay. So E is now the identity of the group, identity element. This is the multiplicative identity. So if E is the identity element of the group, then 1 sub E is the multiplicative identity of the ring K of G. So now let's compute psi of 1E by definition is 1 sub E inverse, but of course E inverse is E, okay. So psi of 1 sub E goes to 1 sub E again. So notice that 1 sub E is a multiplicative identity of kg as well as of kg op, because the identity is always a two-sided identity, right? So whether you multiply it on the left or the right, it doesn't matter, it gives me the same, it serves the role of an identity, okay. So I hope that's clear. So what we have established is that this ring kg op, if G is a finite group, the group ring is actually isomorphic to its opposite, okay. And what does that mean? Well, as a consequence of this thing, we will probably see later that right modules for kg op and left modules of kg are the same thing, okay. So if your ring is kg, then right kg modules and left kg modules are really the same thing, because you can use this isomorphism to take a left module over kg and convert it into a right module over kg op. A left module over kg via this isomorphism becomes a left module over kg op, but a left module over kg op is just a right module over kg, okay. So this in essence the conclusion or corollary of this isomorphism is that for kg left and right modules are really equivalent notions. We don't need to worry about left versus right, okay. Let's move on to problem 2, which is again, let's define a notion for this problem. So define an R module M is said to be simple okay, or a simple R module if it has no submodules, if the only submodules of M are the two obvious ones, 0 and M itself. Okay, so these are the only two submodules. Then we say R is simple. Okay, it has no other non-trivial submodules. So now here's the question. So let's do the following. Let's take the ring to be Cx. C is the complex number Cx, and let's so as you've seen in the lectures, a module over Cx is the same as a vector space over C. So let me take a vector space. So let V be a complex vector space and let T be a linear operator on it. Okay, and we've seen that this data is the, well, what does this data enable you to do? It makes V into a Cx module. So using this, V becomes a Cx module. And what's the additional thing? You really need to specify how X acts, and what we said is that the action of X on any vector is given by the operator T that you fixed. Right. So this was, recall how we make, I mean, every Cx module is of this form. Okay, so I fix a Cx module. Okay, in other words, I fix a complex vector space and a linear operator, and think of V as a Cx module. Prove that this is simple. Prove that V is a simple Cx module. If and only if the dimension of V is 1. Okay, so need to prove that the only way in which V can be a simple Cx module is if its dimension is 1. Okay, so let's prove this. One direction is easy. If the dimension is 1, then V is necessarily simple, because recall, what do submodules look like? So first observe the following. Cx submodules of V are the same thing as T invariant subspaces. So these are just subspaces, T invariant subspaces of V. Okay, i.e. a subspace W of V which has the property that T maps it to itself. This is what a T invariant subspace means. Okay, so if the dimension of V is 1, so now let's prove one direction. So let's prove this direction. If the dimension is 1, then of course there are no subspaces other than 0 and the whole. Then there exists no subspaces, not even talking about submodules here. There are even no subspaces of V other than 0 and 1, 0 and the whole. Okay, so of course there can't be any further submodules. Submodules are subspaces with an additional property, but there are no subspaces even, just 0 and the whole. So of course there are no submodules, so there exists no subspace submodules even. There exists no Cx submodules of V other than 0 and V. So this is trivial. It's the other direction that we need to work on. So if it is simple, okay, you're given that it's a simple Cx module, then you need to show that the dimension has to be 1. Okay, now let's just analyze what a submodule is. So you're given it is simple, right, which means that it has no Cx submodules other than 0 and the whole. What's a submodule? It's just a T invariant subspace, right? So what you're given is that this subspace V, this complex vector space V has no T invariant subspaces, right? That's what's given other than 0 and the whole. Okay, but here is an interesting property of a complex vector space. So I'm thinking of everything here as a finite dimensional complex vector space, so maybe I should have said that. Let V be a finite dimensional, so in this case so let V be finite dimensional complex vector space, and I'm given T, and let T from V to V be given. Okay, so T from V to V is a linear operator, V is a finite dimensional complex vector space. Then here's one thing I know, it always has an eigenvector. Okay, so observe, this just implies that T always has an eigenvalue and an eigenvector. Right? At least one eigenvector is guaranteed to exist. Now, so recall this fact from linear algebra. Now, what does that mean? Let's give that eigenvector a name. Let's call it V. So V is some non-zero vector. When T acts on V, you just get some multiple of V, right, for some lambda, which is what we call an eigenvalue for some lambda in C. Now, observe that the fact that when T acts on V, you get a multiple of V just means that the span of V, so look at the complex span of V. So I'll just write it like this: CV is T invariant. It's a T invariant subspace. This is a T invariant subspace of V. Okay, but the given hypothesis says that there are no T invariant subspaces other than 0 and the whole, but we have clearly constructed at least one T invariant subspace here. This is not 0, it's not the 0 space, so the only thing it can be is the whole. This implies that CV had better be the whole space. Okay, why? Since V is given to be a simple CX module. This is the given hypothesis. Okay, and now you're done, because you've shown that V is just the span of a single vector, which means its dimension is exactly 1. Okay, so that's the end of this proof. Okay, great. Here's an interesting follow-up question. Is the same true over R, the ring of real numbers, the field of real numbers? Okay, so suppose I took I took my ring to be R of X, and I took a real vector space. So remember, I used the fact that there are it's a complex vector space, so it has an eigenvalue, an eigenvector, and so on. So here's sort of follow-up question. Let's call it question problem 2b. Does this hold over the real numbers? So if V is a finite dimensional real vector space and T from V to V is some linear operator that's given, and we think of V as an Rx module where X acts via the operator T. So then the question is, V is simple. Suppose V is simple, does it imply that the dimension is 1? Okay, so observe, the same proof doesn't work anymore, because I don't necessarily have eigenvalues anymore. I don't have real eigenvalues anymore. So which means that I can't necessarily produce an eigenvector, and therefore the same proof won't work. But the question is the result true nevertheless? Can you somehow give a different proof of this fact? Now, it turns out the result is not true in this case. Okay, so here's the interesting observation. No, this is not true. A simple module need not have dimension 1 if you're over the real numbers. And what's a very easy example? Well, we can just take V to be a two-dimensional space. Okay, so I just look at this two-dimensional real vector space R2, and I take this linear operator T from V to V to be, well, I can just describe it geometrically. Let's take T to be the map which is rotation through 90-degree angle, through pi by 2 angle, say an anti-clockwise rotation by a 90-degree angle. Okay, so what does it do? It rotates the plane by 90 degrees. So which means, for example, the x-axis here maps to the y-axis. under the action of this operator t, okay, and so on. So any other line that you pick, so if you took this line here, for example, say at 45 degrees, it will get rotated to the line which is at 135 degrees, and so on. Okay, now this is a linear operator, okay, as is easy to check. And here's the interesting fact: this linear operator has no t invariant subspaces. Okay, this operator t has no invariant subspaces. Other than 0 on the whole. Okay, why is this? Because, well, the total dimension is 2. This is a 0 dimensional subspace. This is the 2 dimensional subspace. What else can it have? If at all it had a invariant subspace, it must be a 1 dimensional space, right? So the question is, can T have a 1 dimensional invariant subspace? What's a 1 dimensional subspace? It's just a line. Okay, so the question is, can I just draw a line somewhere and say, okay, so let's say this one here, I draw a line now and say let's just use some other color. So this is a line. Can this line be T invariant? Well, what does T do to this line? It doesn't map this line back to itself. It maps it to the line which is, at a 90-degree angle to this one. Okay, so just from the geometrical definition of T, it's clear that it cannot map any line to itself. It has to move every line and map it to a different line. Okay, so here is a counter example. If you are over the real numbers, even though this space has dimension 2, this operator is such that V is still a simple module over Rx. Okay, let's move on to the next problem. This is problem 3, which is the following. Again, about simple modules, if you wish. So first, a little definition. So suppose I have M, which is an R module, and if I take an element of M, X in M, then we call, so Rx, by that I mean the space what I get by multiplying X by all the scalars in R. Okay, this guy is called the cyclic submodule. So this is, by the way, a submodule, is called the cyclic submodule generated by X. It's just a submodule generated by X in some sense. So if it's a singly generated submodule, we usually call it cyclic. It's a cyclic submodule generated by X. Okay, now here's the problem. Prove the following. Prove that M is a simple R module. Recall from the previous problem what that meant. M is simple if and only if every cyclic submodule equals the whole module. So by the way, you should check that this is a submodule. It's an easy verification. But the claim is, if M is simple, then every cyclic submodule has to equal the whole. And this is an if and only if. That's where the interest lies. So let's prove this. One direction again is very easy. If M is simple, then recall that meant that it has no submodules other than 0 and the whole, and here is a submodule. Okay, so I should say this is for X not 0, for all X in M other than 0. Right, of course, if I take X equal to 0, it just generates the 0 submodule. So if M is simple, then Rx is a submodule and Rx is not 0, because I have chosen X to be not 0. Therefore, Rx had better equal the whole, because there are no other submodules. Okay, so this is by simplicity of M, by simplicity of M. Now it's the converse that really needs work here. If every cyclic submodule equals the whole, why is it true that M must be simple? Okay, so let's prove that M is simple. So what does it mean? Suppose not. So why don't we proceed by contradiction? So suppose M is not simple. Suppose M is not simple. That means, what does that imply? That means I can find a submodule. There exists a submodule N of M such that N is neither 0 nor the whole. So it's sort of strictly properly between these two ends. So there exists a submodule N which is neither 0 nor M. From this I need to get a contradiction somehow. Okay, so let's do the following. So since N is not 0, let's pick an element, a non-zero element from N. So pick X not 0, X in N. Okay, so take a non-zero element of N and consider the cyclic submodule generated by that non-zero element. Look at Rx. Okay, consider Rx. Now, what do we know? Every cyclic submodule is supposed to be the whole module M. But since X comes from N and N is a submodule, right? What does it mean? If you multiply X, so X is from N and I multiply X by any scalar, the answer is again in N because N is a submodule. Okay, so observe, if I take the cyclic submodule generated by Rx, because X is in N and N is a submodule, Rx is a sub of N. Okay, but N is not the whole space. N is a strict subset of M. So this means in particular that the cyclic submodule Rx can't equal M, and that's a contradiction. Okay, and that contradiction proves what we want.